Yeah.
So today we will have let's say final presentation from Yuka Takahashi. She was working on C++ modules in root and CMSSW for last year, and he will try to present newest results, and basically it will be her final report. So sadly, she will leave us to go back to Japan.
Mm-hmm.
So yeah, please welcome start.
Okay, thanks for having me here. I'm Yuka Takahashi from Princeton and CERN. I'll present a work during my one-year internship on C++ modules. So I have two summary slides for this talk. First of all, the goal of this project was to use the C++ modules technology in root to optimize the performance of experiment software stacks. The achievement of this year is that we released C++ modules in root 6.16, and now we have a working CMSSW infrastructure with root runtime C++ modules. I will give more details in the later this talk, but this is a summary of this year. So for our agenda, first I will present the motivation and background of C++ modules. We will go through system overview and the roadmap that we did in 2018 and the current status and performance on CMSSW. Also, I would like to give some suggestions for future work. So what was C++ modules? In short, C++ module is a mechanism to save C++ headers files, ASP information in PCM file to avoid the redundant header parsing. And this is more into detail. In CMC++, the interface of a library is accessed by including the appropriate header, for example, vector, like this. There are several techniques to implement this feature: Textual Include, PCH, and modules. Textual Include and PCH have some weak points, and modules solve their problems. I will briefly introduce them in the following slides. So for Textual Include, it is basically a copy-pasting. Each #include is expanded to actual text by preprocessor. In this example, each tvirtual pad.h, vector, and set in the original code is expanded to those sections. Textual Include can cause some problems. First of all, it is expensive in terms of the performance. As it is just copy-pasting the header, parser has to reparse the same header again and again. It is fine to do this if it was included only 3 times, for example, in this image, but in reality, it is the same header file is included, for example, 500 times in one translation unit. So the overhead will increase by magnitude if it was included like 1,000 times, which happens in the experiment code. Also, it is fragile. Textual includes are influenced by previously defined macros. For example, in this example, macro pi is undefined in RCPP library. If we include this library, then it is possible to override our local variable double pi with this macro. PCH, precompiled header, is invented as one of the solutions to cope with textual include problems. It precompiles header files and store it in PCH file. However, it also has a weak point that it is not separable because the information is stored in one big file, like this. Finally, with modules, header information is stored in precompiled PCM files. PCMs are separated instead of having a one big file, as in PCH. In our implementation, each PCM file, a.pcm, is correspond to our library, lib.a.so, and it is loaded to interpreter. As a consequence, modules is not expensive, not fragile, and is separable. So let's move on to implementation details. This is a brief diagram. of how root interpreter system works. I'm describing here circles as binaries and square as generated files. First of all, Clang is used as a backend of Clang C++ interpreter. Industry standard C++ module API is provided by Clang, and we are calling this API from Clang. Clang is used from root Clang, which is a dictionary generator for root. It creates dictionary files such as rootmap and rdict. To give a bit of description, rootmap file is a file which is mapping symbols and identifiers to libraries. And rdict is efficiently storing the information needed for I/O serialization. And the generated root dictionaries are being loaded at root runtime. For C++ module implementation is created at this part in the diagram. So root Clang generates root PCMs and root loads them at runtime. As you notice, we have two arrows from root Clang to root via root PCMs and root dictionaries. It is possible that PCMs replace some of root dictionary functions, such as root maps and rdict, as mentioned in the previous slide, with more stable implementation. So this is one of the benefits of root PCMs. The previous slide was the C++ module system implementation inside root, but from now on, it will be about how it is integrated into CMSSW system. So in CMSSW, Scrum build system resolve library dependencies and execute genreflex, which is a wrapper of root Clang, and also Scrum executes C++ compiler such as GCC. Root Clang genreflex generate CMS dictionaries, root maps, and rdicts. At the same time, C++ compilers such as GCC compile C++ files and generate CMS shared object libraries. For CMSSW, we added C++ modules here in this diagram. genreflex generates PCMs, and it will be loaded at runtime of CMSSW. We have now infrastructure working with PCMs. Although not all of the CMS library are modularized, but we already have this infrastructure working. And migration to PCMs can be done incrementally, so this system can coexist with the current infrastructure with CMS dictionaries. Next, I will present the roadmap that we have done in 2018. So I came to CERN in March 2018 and started working on root. For the first 1 month, we were optimizing reflection layer and were reducing easily sized decals. We started working on modules in April, and we spent 3 months working on fixing tests. From July to December, we have been working on performance optimization from root side, and also we released modules in root 6.16 release. From December to now, our main focus was on CMSSW. This is important item, so we will present a detailed current status in the next section. Current status in root and in CMSSW. So on root side, as said, we have a release in root 6.16. We have a support on Linux OS, and recently Mac OS supported was added by Vatil, and we also have green stable nightly builds. Although we have some optimization and bug fixes left on the root side, it is already on a stable state. On CMSSW side, we had 5 stages until the full CMSSW migration to C++ modules. First stage, which is to enable root runtime C++ modules in CMSW was done in the end of December. This means that you can compile and run full CMSW using root, which is compiled with -t runtime cxx module equal on. We have all CMSW and external libraries being compiled, and all tests in CMSW are passing. Second stage, adding C++ module integration build was done also in the end of December, thanks to Shallard. Integration build is regularly run with full CMS build and tests. So before moving to the third stage, I would like to give a bit of explanation for terminology. Implicit PCMs, so this is the difference between implicit PCMs and explicit PCMs. Implicit PCMs are implicitly generated without module maps. It is easy to enable this feature. However, it puts all possible necessary headers into the PCM, so PCM size become humongous, and it contains a lot of header duplication. However, with explicit PCMs, we need to have an infrastructure called module map. Explicit PCMs can be generated by introducing module maps, and this is one example of module map inside root, which is a module mascore.pcm. It is like a definition file of header for PCMs, and as it explicitly defines which header should be in the particular module, it reduces the header duplication between modules. So the third stage, generating implicit PCM for CMSW was done in January. It means that genreflex with flag --cxx module works in CMSW. As mentioned in the previous slide, implicit PCMs have a huge size coming from header duplications, and these problems will be solved by introducing module map, which is in the next slide. So the fourth stage, which is still ongoing, is to generate explicit PCMs for CMSW. We have now 25 libraries modularized out of 107 data format libraries. It took me 2 weeks to modularize first one library. It involves making changes in root and CMSW infrastructure, but these heavy constructions are already done, and modularizing the other remaining libraries can be done by manual procedure. Finally, we have fifth stage, which is to generate explicit PCMs for external libraries. We didn't have to get this working in 3 months, so this is kind of a future work. But Raphael, who was a technical student, worked on C++ modules 2 years ago, created a compilation time module map for Boost and other external libraries such as libxml. This module map needs to be refreshed and to be integrated to the runtime system, but at least we have a fundamental starting point for this project, this future project. So let's move on to performance results. We have 3 different builds which we measure performance on. First one is CMSW with root master. This is basically the root master with CMSW. And the second build is CMSW only with root PCM. So it loads root PCM such as core.pcm, rio.pcm, masmore.pcm, and etc. And the third build is CMSW with root PCMs plus CMS PCMs, which is generated by genreflex. And we currently have 25 CMSW PCMs being loaded. For example, data formats common.pcm, data formats mass.pcm, and so on. Just to provide a color to see the difference. And so following 6 slides of fresh performance measurement with explicit PCMs, which has now 25 libraries modularized. These are very new measurements, and we need to study more to actually understand whether the differences come from modules or not. So this measurement is CMSW with root master with 2018 CMS detector digitization with PyLab test. we are measuring 10 events and taking average of 5 times execution. This is CMSSW with root PCM, so it means that it's loading root PCM such as core and TMVA. And this is also measuring 2018 CMS detector digitization with PILOT. Same test, but with loading CMS PCMs. This is the comparison between the root master. We see some performance improvement, kind of, but we need to study more to actually investigate the result. This is another test, which is 2015 detector CMS digitization workflow on root master. This is the same test with loading root PCMs. And this is the same test with CMS PCMs. Also, we see kind of improvement in the same measurement. So for Akkad 2019, which will be held in the middle of March, we are planning to make more progress towards CMSSW. We need to extend the test result and to increase the number of events, because now we are only testing with 10 events. And thanks a lot for David and Shazad in terms of CMSSW for advice and explanation and spending a lot of time on this. So finally, I would like to suggest a future roadmap to make C++ modules enabled by default in CMSSW. To generate a remaining explicit PCMs, which means to write a module map for CMSSW, would be a good project for full-time student FTS for 2 months. Implementing a global module index and to generate explicit PCMs for external libraries such as Boost and libxml will be a good project for 3 months full-time student. I will explain a bit more about global module index in the next slide. So global module index will further remove an overhead at startup time of root. It is a mechanism to create a table of symbols and PCM names so that we can look up when necessary. We already have a prototype which shows a promising results. Also, reducing the header duplication for optimization will be a good project for 3 months full-time student. So for my remaining 2 weeks, I'm planning to write documentation, prepare for the Akkad talk, and also to upstream all the changes that we've done to CMS repository. Finally, thank you so much for everyone involved, especially Vasil, Oksana, Shazad, Axel, David, Mutual, and Rafael, and all the root team. Thank you.
Thanks.
Thank you very much, Yuka.
Oh,
I just wanted to see if I get a chance to really thank Yuka for all the work she did. Without her invaluable help, we wouldn't have been, the root team wouldn't have been able to make the good progress on the PCM that we have been able to do. I think she has provided a very valuable and very necessary help. Thank you very much, Yuka.
Thank you.
thanks, really. If there is some questions from outside.
This is Vasil here. I just wanted to second what Philippe said. I was very happy to have you, and hopefully you will continue in one form or another your relationship with CERN and the field. And I think soon after you leave, and this is the weird part of it, we will be even more grateful of this work that you have been doing for us. So once again, thanks.
Thanks, Vasil.
I guess I have a question. The actual module map files, that
Yes.
that is also required for the proposed C++ standard for modules. Is that correct?
For C++ standard, there is no such thing as module map, as I understand.
There is a file, but okay, go ahead.
Can I just quickly comment? So there in the modules TS that hopefully is going to be merged this week in the working paper of C++, there is a section which is defining the legacy header support, which means that it gives an incremental path to enabling modules for a non-modular code base. And the module map is one way to implement this legacy support, and I see GCC converging towards something similar. Nathan Sidwell is working on this feature, and he has a flat version of the module map, which I think he is going to turn into a module map, because there is no way how else you can implement submodules. But the standard doesn't explicitly standardize the module map.
All right, thanks.
More questions?
The number we have seen, do you know if that improvement was in startup or during the event loop?
Yes. Wait. Okay.
I'm just wanting to know if it's just one-time gain, or if we run it for more events, we'll see more performance.
It's early to conclude about the performance, because it's like very immature measurement. But from here,
It is not from init.
yeah, it is not from init. The performance gain is from event setup get.
But most of the dictionary we read during the initialization, right?
No, a lot of the dictionaries also get handled in the first event request, which would be in the event loop, so it's hard to know.
Okay, after first, we will not be doing a lot of that, right? Most of them are read during few events, right?
Right, so what you would need to do is like run 10 events and then run 100 events and see how that scales. My guess is that the time differences will be constant, not improve as the number of events grows. But still helpful.
Yeah.
Well, I think we are repeating in CMSSW at least. This is the first time that I see these measurements, to be honest. But what it looks to me is that we are repeating the experience that we have with root. So the first version is something that's very non-efficient, and then slowly and gradually improving the performance. We can gain a lot, because right now we're doing a lot of work that we don't need to. For example, we are reading things like root map files. We have duplications in the modules and all this. We don't know how it's going to manifest performance-wise. We do know that it's going to be less, but we don't know how much less it would be. And it could be less orders of magnitude, because, for example, as Yuka mentioned, some of the PCMs are 3.2 gigabytes, and this is where exactly we started with root. We had the overall number of PCMs were around 2,000, and it was like 2 gigabytes of PCMs. Right now, our PCMs are 200 megabytes, which can go down even more, and they are super efficient. So I would expect that we can get an order of magnitude here.
Now, my only worry is that, okay, now mostly we run our software from CMFS. And okay, if these PCMs are bigger in size, so you will be reading from network, and then okay, you might be hitting your CMFS cache limits, and you're reading these files over and over again.
This 3.2 gigabyte will not stay. This is
no, even if it goes to 1 gigabyte, it still is a network traffic, right? CMFS has to cache these files and kick them out because your local cache is filled. So we need to see how it goes. But
I doubt it will be more than a few hundred megabytes because we have 80 or more dictionaries in root, and there are 200, and they have a lot of duplications. So we can go further down. So if CMS dictionaries are 200, from what I see, then probably we can get to half a gigabyte or something.
And also, for example, with C++ module, we have like a possibility to not generate root map and rdict. Will be able to kind of like not generate them. So if you compare these like size of files with, so I think it will compensate.
So I hope you will stay a bit around. I mean, just keep on in touch and check out. I hope you will get your GSOC student. Yuka applied for Google Summer of God student. That should help to implement
global module index.
Yeah, and this how we try to keep her around. Okay, thanks. And if there is no questions from outside, then we will say that this meeting was short.
Thanks, Yuka. It was really nice meeting you, and it really helped us. We still have to finish that work, but I hope that it's just that somebody needs to go through all these 200 libraries to make module map otherwise.
Exactly. Or we implement this classes.h thing.
Yes.
Yeah.
A root map file, no, the module map file is still handwritten, right?
Oh, no, like if we have this classes.h thing, module map can be automatically generated. Like, of course, we kind of like need to go through like not each header, but each library.
We're already doing this. No. I think Rafael works actually contains something that.
No, but that was yes.
So I was reading this to generate them because CMSSW changes, and when I had to.
Yeah, but this module map was for compilation time, so it doesn't I initially used this module map for runtime, but it kind of didn't work. So for runtime, we need to have something like auto-generated from classes.h. So.
Okay, so then people outside see you for next time, or it's already disconnected?
No, we're not.
Yeah. Okay.
Bye.
Okay. Thanks everyone.
Thank you. Bye bye.